In this video, we are going to continue with science paper 1 for the year 2017. Now, this paper was written by the internal. Now, we'll consider this video as part 2 since we are beginning from question 3. So, let's look at question 3. Figure B 3.1 shows some energy conversion in a coal-powered station. So, we have a station that works on coal. Now let's analyze this station. So here we can see that the total amount of energy which was put into this system was 1000 joules. Then we have the first part here where we are told that we have a boiler turbine generator. Now when this 1000 joules passed through this boiler turbine generator, 70 joules was wasted in friction. So from that 1000 we need to subtract a 70 joules. So we have 930 joules. Then from there we have that 930 will pass through the cooling tower. So from this cooling tower a certain amount was also wasted. We don't know what amount was wasted here, but we just have the picture that there was a certain amount of energy that was wasted here. Then from there, the remaining after this amount of energy was wasted passed through the transformer, where another 30 joules wasted in heating the wires. Then from there, from the 1000, we can see that the output, the energy that was produced was 300 joules. Now let's look at the first question here. How much useful electrical energy is provided by the power station? So from this 1000 energy as our input, the 300 joules was our output. So this is our answer here. So 300 joules was produced as the useful electrical energy. Now let's move on to question B. Calculate how much is wasted from the cooling tower. Okay, now let's look at what we have here. So the input, the total amount of energy that was generated or that was put into this system was 1000 joules. Then from that 1000 joules, 300 was produced as the output. This means that if we subtract 300 from 1000, this indicates that the 700 joules was wasted. If 700 was wasted, how much from that 700 was wasted at the cooling tower? So let's look at the two energies that we have. So we can see that we have the 30 joules that was wasted at boiler turbine generator and 30 joules that was wasted at heating the wire. So if we add these two, 70 plus 30, this will give us 100. So we have the picture that the total amount of energy that was wasted was 700. Now from that 700, we have this 30 plus 7, which is giving us 100. So 700 minus 100, this indicates that here there was a 600 joules that was wasted. So the calculations that we can make here is the total amount of energy that was wasted was 700 joules. Then we are going to subtract this 70 plus 30. So we have 70 joules plus 30. So this will give us 700 joules minus 100 joules, which will give us 600 joules. So this 600 joules was the total amount of energy that was wasted at the cooling tower. Now let's move on to question C. Calculate the efficiency of the power station in the production of electrical energy. So the efficiency, the formula for efficiency is So we are going to say energy output, since we are dealing with energy. So we'll say energy output divided by the energy input. Then multiply by 100%. So the energy output is the total amount of energy that was produced. So from that 1,300 was produced. So this is our energy output. Then the total amount of energy that was put into this system was 1,000 joules. So this is our energy input. This is our input energy. So over 1,000 joules multiplied by 100%. So if we cancel this, we can see that we have 3 over 10 times the 100%. So if we divide the 3 divided by 10 will give us 0.3 times 100%. This will give us 30%. So this was our efficiency. So from this we can see that the operation of system was not that the efficiency of that system was bad, since we can see that 70% of energy was wasted. So this is how we can calculate a question like this one. Okay, so now we move on to question 4. Figure B 4.1 shows a cylinder containing a gas of volume 5 cubic centimeters at a pressure of 100 kilopascal. The piston is pushed to half the original volume at the same temperature as shown in figure B 4.2. So we have the first structure here, and also have the second structure. Now from the second structure we can see that the piston was pushed in this direction. So what this means is, as the piston was pushed, the particles now are becoming closer to each other compared to the way they were in the first part here. So in this first picture here, we can see that the particles, they are far apart from each other. Now if we look at gas pressure, we are looking at the collision of the particles on the inside surface or the container. So these particles, we know that particles are in random motion, so they are always moving. So as they are moving, they are colliding with each other, and also they are colliding with the surface of the container where they are. So from the first picture here, we can see that there are some spaces, so the collision is not that high. But from this structure here, we can see that they are closer to each other, so the collision is higher in the second picture compared to the first picture here. Now let's look at the first question, question A. We are taught to state Boy's law. So this law states that the volume of a fixed mass of gas is inversely proportional to the pressure acting on it. So at constant temperature. So this is one of the way in which we can state what the Boy's law. So this law is giving us the relationship between pressure and volume, given that the temperature remains constant. So the relationship between the two factors is that they are inversely related. So inversely related means that if one factor increases, the other one decreases. So we can see from this picture here, this picture tells us that the volume is greater than this picture here. So when the volume is greater, the pressure becomes low. The collision of particles becomes low. But if for this one here, if we decrease the volume, if we try to decrease the volume, we can see that by pushing the piston in this direction, we can see that the size, the volume is decreasing, but the particles are becoming closer to each other. The more they become closer to each other, the greater the pressure or the collision effect. Now, for the formula for Boyle's law, we use the pressure 1 multiplied by volume 1 is equal to pressure 2 times the volume 2. So that is the formula. You need to master this formula here. Now let's look at the data that we have. Let's look at the pressure 1. So the pressure before the piston was pushed, the pressure was 100 kilopascal. So this is our pressure 1. So 100 kilopascal. Then the volume was 5 cubic centimeters. Then we are solving for pressure 2. Now, what was the volume 2? So let's look at the question. The piston is pushed to half the original volume. So the original volume is 5 cubic centimeters. So what is half of 5 cubic centimeters? So the half now is 2.5 cubic centimeters. Now, the relationship here is these two numbers must go in the same proportion. So we can see if we can analyze this one. So the initial volume, the volume before the piston was pushed was 5. Then we can see that after the piston was pushed, the volume became 2.5. So we can see that the volume decreased by half. Then let's look at the pressure. So the pressure was 100. What do you think would be the pressure, the second pressure? Since we are saying if the volume decrease, the pressure must increase. Now, by what factor was this 5 decreased to 2.5? So we can see that if we divide the 5 divided by 2, we get 2.5. So for this one, we are going to multiply by 2. So we are expecting to get the number of 200. So that is the picture here. So now let's prove by this calculation here. So let's multiply 5 times 100. We have 500 kilopascal. Then cubic centimeters from this. Then 2.5 cubic centimeters times P2 is 2.5 cubic centimeters. Then pressure 2. What do you do? We divide by 2.5 cubic centimeters. Then also here we divide by 2.5 cubic centimeters. So we cancel. We have pressure 2 is equal to, so we cancel this, we cancel this. So we can now divide the 500 divided by 2.5. So from my calculation, I'm getting 200. So that is our final answer. So 200 kilopascal. So this was the new pressure. Okay, so now we move on to question C. Use the kinetic theory to explain why pressure increases in the cylinder's volume decreases. So like we said earlier, from the diagram, we saw that from the first diagram, the volume, the space, the amount of space was 5 cubic centimeters. Then from the second diagram here, we saw that the piston was pushed to half of the original volume. So we saw that the particles became closer to each other. So this kinetic theory, we are looking at the behavior of the particles when we have, let's say, two cylinders having different volume but having the same amount of particles. So from the diagram A, so consider this one as diagram A, then this one will be as diagram B. So from diagram A, we can see that the volume is greater than diagram B. Now, if the volume is greater, how are the spaces in between the particles? So we can see that we have at least large spaces between the particles. Now, what happens if we decrease the volume? So if we decrease the volume, this simply means that the particles are coming closer to each other. We can see from this diagram B. So as the particles are becoming closer to each other, so is the collision effect. So it is easy for particles to collide with each other and with the whole of the container if the spaces are very, very small. So this is the concept that we are trying to use here. So we'll say as the volume decreases, will result in smaller spaces between the particles. And this will also result in higher collision of the particles. So the key point here is when you decrease the volume of a gas, the pressure increases, and the reason why the pressure is increasing, the collision is increasing between the particles and also of the particles with the wall of the container. So as the volume decreases, will result in smaller spaces between the particles. Then there is something that I want to share with you about these gas laws. Now, for some people, it is difficult to maybe memorize the formulas that are given. So there is this formula that I want to share with you that can help you you can construct any of the four formulas from this formula. So the formula here is we use T is equal to PV. Now, let's say we are dealing with Boyle's law. So if we are dealing with Boyle's law, the first thing that we need to consider, remember, there are three factors that we are putting into consideration. The first factor is the temperature. Then we have pressure. After pressure, we have volume. So these are the three factors that we are only interested in here. Now, if we are dealing with Boyle's law, temperature remains constant. So if the temperature remains constant, we also saw that the relationship between pressure and volume was inversely related. Then let's look at what are we supposed to do after identifying that the temperature is constant. So whenever you are given a question, the question will always tell you the factor that is constant. So in our case, if you are dealing with Boyle's law, temperature is constant. So you need to make the factor that is constant the subject of the formula. Now in our case, temperature is already the subject of the formula. So what you are going to do is this part here must be substituted where there is T. So this will give us PV is equal to PV. Then we are going to make the first one, we'll consider them as our initial, but we use the numbers 1 and 1 here. So pressure 1 times volume 1 is equal to pressure 2 times volume 2. So this is how we can construct the formula for this one. Now let's say we are given a question for Charles' law. So if we are given a question for Charles' law, also we need to look at which factor is constant during the Charles' law. So pressure is constant. If pressure is constant, from this formula that I've given you, let's make P the subject of the formula. So we are making whatever that is constant the subject of the formula. So whenever we want to isolate P, we are going to divide both sides by V over V. So if we cancel, we know that P is equal to T over V. So since we have now P as the subject formula, whatever that has formed after the equal sign should be substituted here. So the formula for Charles' law will become T over V is equal to T over V. Then we'll consider this temperature 1, volume 1, temperature 2, volume 2. This formula is the same as if we want, we can make the volumes as our numerator while the temperature as our denominator. The formula still remains the same. So you can say volume 1 over temperature 1 is equal to volume 2 over temperature 2. Now let's look at Lussaki's law. If the question is about Lussaki's law, Lussaki's law. So under Lussaki's law, the volume is constant. So let's go back to our formula. So our formula is T is equal to PV. So this time, let's make V the subject formula. So we divide by P, also here by P. So we can say that V is equal to T over P. So here we are going to substitute with this. So this will be T over P, T over P. Then we'll consider this as temperature 1, pressure 1, temperature 2, pressure 2, or pressure 1 over temperature 1 is equal to pressure 2 over temperature 2. So we can see that from these three laws, each law has a factor that is constant. So from the Boyle's law, temperature is constant. Charles' law, pressure becomes constant. Under Lussaki's law, volume becomes constant. So if volume is constant, pressure and temperature will change. If pressure is constant, volume and temperature will change. If temperature is constant, volume and pressure will change. So this is the pattern under these gas laws. Now let's look at an ideal. If we are looking at ideal, under ideal gas equation, there is no factor that is constant. All three factors will change. So how can we drive the formula for ideal gas equation? So we'll say T is equal to PV. Now we know that even T is changing, P is changing. So there is no factor that is constant here. So what we are going to do is we need to remove this T so that every factor will be here. So what we are going to do is we are going to divide by T, also here by T. So that if I cancel here, I have 1. 1 is equal to PV over T. Now where there is 1, we are going to put this. So the ideal gas equation is PV over T is equal to PV over T. Then we use 1, 1, 1, then 2, 2, 2. So these are the formulas for these laws here. So this is one of the ways that may help you to construct, especially for those that may find it difficult to master them the way they are. You can use, see, the key point is you need to master this. T is equal to PV. So during exam, my advice is when you are going for an examination, as soon as you start writing that, you may find a paper where, I'm not saying malpractice, but you may, maybe from the question paper, you can write it somewhere there before you forget it. We move on to question 5b. The question here, we are looking at the human audible frequency range is 20 Hz to 20,000 Hz. The speed of sound in air is 330 meters per second. So now, Roman number 1, what is the upper limit of the human audible frequency in kilohertz? So we have this audible range, and this range is from 20 Hz up to 20,000 Hz. Now this one is considered as our lower limit, while this one is considered as our upper limit. So what this means is beyond or above 20,000 Hz, the human has no ability to detect sound, and below 20 Hz, the human being cannot detect sound. So the human has the ability to detect sound from the 20 Hz up to 20,000 Hz. Now, let's go back to our question number 1. What is the upper limit of the human audible frequency in kilohertz? So we want this number in kilohertz. So the word kilo means 1,000. So what this means is 1 kilohertz is equal to 1,000 Hz. So this 20,000 Hz will be written here. So we have 20,000 Hz, then we put x, then we cross multiply so that we can solve for x. So 1,000 Hz times x is 1,000 Hz x. Then here we have 20,000 Hz times kilohertz. So we divide by 1,000 Hz over 1,000 Hz here. So we can now cancel x is equal to this. So we divide by 20,000 divided by 1,000 is 20 kilohertz. So the 20,000 Hz in kilohertz is 20 kilohertz. So that is the answer here. Now to summarize our point here is we have said 1 kilohertz is equal to 1,000 Hz. So if you are converting from kilohertz to Hz, you multiply by 1,000. Then the reverse is also true if you are converting from Hz to kilohertz. So this time you divide by 1,000. So whenever you have a number in Hz and you want to convert it into kilohertz, just divide by 1,000. Now let's move on to Roman number 2. Here we have the question that is asking us to find the wavelength of the lower limit. So the key here is the lower limit. So this means that we are going to use the frequency for the lower limit of the audible frequency range. So let's use the formula. We know that the speed is equal to frequency times the wavelength. So what is the speed? We know that we have been given the speed of the sound. So the speed is 330. So where there is V, we put 330 here. Then the frequency. What is our frequency? Since we are told the lower limit here, we are going to use the value for the lower limit, which is 20. So our frequency will be considered to be as 20. So 20 times this symbol lambda. So 20 times lambda, we have 20 lambda here. We divide by 20, also here by 20. So if we cancel, we know that lambda is equal to, so what is 330 divided by 20 or 33 divided by 2. So I'm getting 16.5. So since we are solving for wavelength here, we are going to get meters as our answer. So this is one way of which we can calculate the wavelength given the frequency and the speed. Okay, so now we move on to question 5b. Figure B5.1 is a diagram of wave traveling through air. So we have in this axis there is displacement, then we have 4 distances, one denoted by W, we have Z, X, and Y here. Now let's look at the first question here. We want to find the distance representing one wavelength. So wavelength is just the minimum distance between 2 points on the wave, or we can say wavelength is just the total distance covered by one complete wave. So let's look at these distances. This is not the wavelength because it is giving us the distance, or it is giving us the amplitude. So this is the amplitude. Then for this one, this is not also the wavelength. Then let's look at this line for W. So let's look at where it is beginning. So it is beginning from here. So this part and ending here. So this part here and this, if we combine these two, will give us the half. So this is 1/4, this is 1/4, and this is also 1/4. So if we add quarter plus quarter, so quarter is 1/4. So if we add 1/4 plus 1/4, this will give us half. So we can say the lowest common denominator is 4. 4 into 4 will give us 1 times this one here, 1 plus 1. So 1 plus 1 will give us 2/4. If we reduce 2 into 2 is 1, 2 into 4 is 2. So we can see that these 2 will give us half. So we have half plus this one will also give us this is half plus half. So if we do the mathematics, this will give us 1 plus 1, which is 2/2. So this will give us 1. So we can say that the distance from here up to here is giving us a complete wave. So the answer for Roman number 1 is W. Because this Z is not making one wave, we only have this half here plus a quarter. So we have 3 quarters, or 3/4. Then let's look at Roman number 2, the amplitude of the wave. So the amplitude is just the maximum displacement of a point in the wave from its rest position. So this line here indicates our rest position. So the distance from here up to here is our amplitude, or this one. We just know that this distance here is equal to this distance. So we'll use now letter X. So this is how we can answer this question. So move on to question 6. Figure B6.1 is a diagram showing the appearance of a coin immersed in water when viewed from above. So we will have the coin here. Then when viewed up from above, the coin is appearing to be here. So there is what we call the real depth. So the real depth is the distance from the surface of water to where an object is. So the surface of water is here. This is our surface of water. Then the point where the coin is here. So this 15 centimeter is our real depth. It is telling us the real distance or the height. So we have our real depth. Then the apparent depth is the depth that appears to be true, but in actual sense it is not. So this is our apparent depth. So the coin is appearing to be here, but in actual sense, the coin is there. Now let's look at the first question here. The first question will have state Snell's law. So there are two ways in which we can state the Snell's law. The first one, I will just say this. So you can state that the incident ray, comma, the refracted ray and the normal ray at the point of incidence all lie in the same plane. Then the other one that you can use is the ratio of the sine of the angle of incidence to the sine of the angle of refraction is always constant. So those are the two Snell's law. Now let's look at B. What happens to the rays of light at the surface of water in figure B 6.1? So the direction of these rays is, this is our direction. So this means that these rays of light are coming from a more denser medium, which is water, into a less denser medium, which is air. Now we want to look at what happens if rays of light moves from a more dense medium into a less denser medium. So the first one, we are going to draw a normal ray here. So this is our normal ray. So make sure that the normal ray must be perpendicular to the surface or to the reflecting or refraction surface. So these two are normal rays. Now we can also see from the diagram that this ray of light and also this one, so these two rays of light were refracted or bent away from the normal ray. So this is what we need to say whenever we have a question like what happens to the rays of light at the surface of water in figure. If as long as the rays of light are coming from a more denser medium into a less denser medium, they will always bend away from the normal. So we'll say the rays refracted away from the normal ray. So that is the point that you need to have in mind. If the ray of light is moving from a less denser into a more denser, it will bend toward the normal. But if it is moving from a more denser into a less denser, it will bend away from the normal. So that's a picture here. Now let's look at question C. Question C here, we want to calculate the refractive index of water. So we will calculate the refractive index based on the data that we have. So from this diagram here, we can see that we have the real depth and apparent depth. So refractive index is of water given real depth and apparent depth is equal to, so the real depth should be on top divided by the apparent depth. So the symbol for refractive index is small letter n. Then real depth here, this is 15 centimeters over the apparent is 11.28. So we can see that we can cancel the centimeter. So let's do math. So 15 divided by 11.28. So according to my calculation, I'm getting 1.329787. Then our final answer will say 1.3. So we're going to round off these two. This will become 3. So the refractive index of water is 1.33. You can also commit this answer to memory so that as you are making calculation, even if you are whatever question may be asked, the point is the refractive index of water is always 1.33. So we move on to question 7. Figure B7.1 is a circuit diagram with two resistors connected to a 3 volts power supply. So let's look at we have this resistor, then also this resistor here. We also have the A for ammeter. Ammeter is used to measure current. Then the power supply here, we can see that 3 volts was produced. Now let's look at the first question. Identify the type of circuit arrangement of the resistors shown in the circuit above. So the question is asking us, what type of arrangement is this? A series connection or parallel connection? So we can look at the arrangement of the resistor. So we'll call this one as our resistor 1, then this one as our resistor 2. So we can see that these two resistors are in the same straight line or in the same loop. So this is what we call the series connection. So we have a series. Now the parallel connection is like this. Let me see if I can give you a picture of the difference between it. So whenever you see this is what we call the parallel circuit. So you are able to see the difference. So we have the 2 ohms here, then also 2 ohms here. So this is what we call the parallel. Then let's move on from this question to question B. Question B, we want to calculate the total resistance in the circuit. So how do we calculate the total resistance or the effective resistance or the combined resistance given that the circuit is connected in series? So the formula is very simple. You just have to add the two resistors that we have. So we'll say total resistance is equal to resistor 1 plus resistor 2. Total resistance is equal to resistor 1 is 2 ohms plus another 2 ohms here. So our total resistance is equal to 4 ohms. Now we can move on to question C. Now before we move on to question C, let's see if we can redraw the diagram. So let's see what we've done here. So the picture here is we are saying we've combined these two resistors to make one resistor. So that is what the picture is here. So this means that the combination of the two resistors will give us the connection where we have 4 ohms. So this is the picture whenever you are trying to find the total resistors. Now let's look at question C. Calculate the ammeter reading. So the ammeter reading is we are trying to find the current that was being measured by the ammeter. So current is equal to voltage over total resistance. Since we are calculating the total current, we need to use the total resistance. So the voltage, we know that we have 3 volts over, then for total resistance, we know that we've calculated 4. So over 4. So what is 3 divided by 4? So I'm getting 0.75 amps. So this is how we can calculate the current. We move on to question 8. A cell phone charger has a transformer with 2000 turns in the primary coil, which converts 240 volts AC to 6 volts AC, and a rectifier that converts 6 volts AC to 6 volts DC. So let's look at the first question. What do the letters AC and DC stand for? So AC stands for alternating current. An alternating current is the type of current that changes direction periodically. Then there is no specific direction under alternating. Then for DC here, this is a direct current. Under DC, the current has a specific direction. You can see the flow of current. Now let's move on to question B. How many turns are in the secondary coil of the transformer? Now let's look at what type of a transformer are we dealing with. So we are dealing with a step down transformer. Why? The input voltage was 240. Then this transformer was able to produce a 60 volt. So the voltage on the primary coil is 240, while the voltage on the secondary coil is 6 volts. So whenever you have a lower voltage on the secondary coil than on the primary coil, you are dealing with what we call a step down transformer. So now the picture under the step down transformer, we know that the number of turns on the primary coil is 2000. So we are expecting to have the less number of turns on the secondary coil. So now let's look at the mathematics here. So by what number was this 240 divided with in order to get 6? So for us to find this number, we are going to divide by 6. So 240 divided by 6. So if you divide the 240 divided by 60, you are getting 40. So this means that this number here was divided by 40. Then for them to get this 6. So the same pattern will also happen to the number of turns. So the point here is the number of turns and the voltage moves in the same proportion, or they use the same ratio. So whatever that happens to the voltage or the number, if it was divided, then you do the same to the number of turns. If then the voltage was multiplied by the same number, you use the same number to multiply the number of turns to have the number of turns on the secondary coil. So meaning here we are going to divide by 40, so that if we cancel this, we cancel this. Then 4 into 200 or 40 into 2000 will give us 50 turns. So we are expecting it to have 50 turns on the secondary coil. So maybe how can we solve this number? We can also solve it like this. So we can say 240 on the primary coil will have 6 here. Then you have 2000. Then we can put x here. Then we can cross multiply. So 240 times x, we have 240x. Then here we are going to have 6 times 2, we have 12,000. So let's divide it by 240, also here 240. So x is equal to, if you divide the 12,000 with 240, you get the same answer, 50. So you can answer it like this. So we have 50 turns. Or if you want, we can use the equation where we use the number of turns on the primary divided by the number of turns on the secondary is equal to voltage on the primary over voltage on the secondary. So number of turns on the primary we have been given is 2000 turns in the primary coil. So we have 2000 over number of turns on the secondary is what we are solving for here. So just leave it like that. Then voltage on the primary is 240. So we have a 240 volts over the voltage on the secondary is 6 volts. So we have 6 volts. So we can see that we'll still get the same answer. So 240 volts NS is equal to 6 times 2000, we have 12,000. We divide by 240 here, also 240 here. So you can see that number of turns on the secondary coil is equal to 50. So this is how we can answer a question like this one. Okay, now move on to question C. Draw a label diagram of a step down transformer. So the first one, we are going to draw this iron core. So say soft iron core. Then since we are drawing a step down transformer, we are expecting to have more turns on the primary coil. So you just have to make sure that there are more turns on the primary coil. So we have the primary coil here. Then on the secondary coil here, we need to have less number of turns. So we have the secondary coil here. So this is our structure, or we can also draw the transformer like this. So where the primary coil, we can show this is our primary coil. Then here we are going to have our secondary coil. So the key point whenever you are drawing a transformer, depends on the type of transformer. You need to make sure that one coil has more turns than the other. So this is how we can draw the structure. Okay, so now we move on to question 9, the last one for section B. So B9, the symbol U, uranium, with a mass number of 238 and the atomic number of 92, represents a nucleus of uranium with nucleon number 238 and proton number 92. State the meaning of the nucleon number. So nucleon number is the other name for mass number. So this question is the same as state the meaning of the mass number. So mass number is just the total number of protons and neutrons contains in an atom, or contains in the nucleus of an atom of any element. So say this is the total number of protons and the neutrons found in the nucleus of an atom of a given element. So the key point is the mass number or nucleon number is just the sum of the protons and neutrons contains in the nucleus of an atom. So this is how we can define, or how we can give the meaning of the mass number or nucleon number. Remember, the nucleon number is the other name for mass number. Now let's move on to question B. A nucleus of uranium 238 decays to form a nucleus of thorium by emission of an alpha particle. State the proton number of alpha particle. So for us to have a clear picture, first let's indicate the decay equation for uranium when it emits an alpha particle. So we'll say uranium, we have been given the symbol is U, then the mass number 238, the atomic number 92. So uranium is the parent atom because it is what is forming the daughter atom, and the daughter atom here is the thorium. So the symbol for thorium is TH plus we need to write the notation for alpha, where we put 4 here, also we put the 2 here. So now what are we supposed to do to the mass number? So whenever we hear that an element emits an alpha particle, the mass number we need to subtract 4. So 238 minus 4, we get 234 here. So make sure that this number plus this number, if you add these two numbers, you need to get the total here. So that is the picture there. Now let's look at what are we supposed to do to the atomic number. So the atomic number, we are going to subtract 2. So 90 minus 2, here we have 90. So you can see that even if we add these two numbers, we need to support, we are supposed to get 92. So this is a decay equation for the emission of alpha particle. Now let's look at the question. Number 1, the proton number of alpha particle. So the proton number of alpha, this is our alpha particle. So the proton number is just 2. The proton, you need to just get the number here. So that is our proton number. Then the nucleon number of alpha. So the nucleon is the mass number. So this is our mass number for the alpha. So we have 4. Then the proton number of thorium. Thorium is what is formed here, the daughter atom. So the proton number, we need to get this number here, 90. So we have 90 here. Then the nucleon number of thorium. So the nucleon or the mass number here, this is our 234. So this is how we can answer this question. So that's it for this video. God bless you.